Last week, I was online with a student who was asking some really good questions about the PV diagram and visualizing the PV diagram. So that inspired me to create another module sort of dedicated to that topic. So let's get started with reviewing a little bit about visualizing the critical point on the PV diagram that has the vapor dome for phase change substances. So let's do a little quick review about what you already know about phases. Let's combine your Common Sense 101, things that you already knew before you signed up to take this class, coupled with what you're learning in ME 2134. So let's see, phases of H2O. You already knew about ice. You already knew that H2O ice is in the solid phase. So the solid phase of H2O is ice. How about a bucket of water? You're very familiar with a bucket of water, of course, but now you know the jargon. You say, what's in that inside that bucket of water is compressed liquid. The phase of the H2O is a compressed liquid. A pot of water boiling on the stove, it's reached the boiling point and it's come to a rolling boil. Of course, you know how to describe that with your common sense, but now you know to describe it in the thermo jargon. It's a saturated two-phase mixture of saturated liquid. What you see is the water, and saturated vapor. What you see is those bubbles. And then finally, you also know that you can't really see steam, can you? But certainly in this little image, I'm trying to depict steam that's coming out of a steam pipe. And what you see with your eyes, that cloud that you see, it's not really steam. It's really steam that's condensing back into liquid. So we went ahead and then in class we talked about let's draw a pressure volume diagram that represents a phase change substance. Let's say like H2O, could be CO2, couldn't it? Could be helium. But in general, we've been doing a lot of talking about pressure on the Y, specific volume on the X. This green line is the vapor dome. And that student online asked, what's the meaning of the top of the vapor dome? He said, I think I get the phases. I've learned what the names of the different phases of a phase change substance like H2O are relative to this green line, relative to this vapor dome. But sort of what's the meaning of the top of the vapor dome? Well, of course, that's called the critical point. I think you know that. But on this module, I'd like to do some specifics. I'd like to look up some numbers, to assign some numbers related to what you already know about H2O and see how that relates to things you already know about H2O. We also talked about the TV diagram, didn't we? We drew a vapor dome on the TV, the temperature specific volume diagram. Of course, the phases of the substance are very similar to the PV diagram. And of course, the top of the vapor dome, of course, is the critical point. And so what I'd like to talk a little bit about and help you visualize is, what does the critical point really mean? What does that mean? What does that red dot mean? And how can I visualize? Is there a way I can visualize the critical point on the vapor dome? Well, let's get started by going to table A1 in your book, and we'll browse down to near the bottom of that table and we'll find water, H2O, and let's just write down what the critical properties are for H2O. I see in temperature, the critical temperature is 647 degrees K, and the pressure is 220.9 bars. Now, I got to tell you that 647 degrees K, that doesn't mean a whole lot to me. I don't have a physical feel for that. But 220 bars, about one atmosphere, about how many bars are in one atmosphere? About one. So 1 bar is about 1 atmosphere, or about 100 kPa. Those three are all about the same. And so for water, the critical pressure is really, really high pressure, 220 bar compared to 1. All right, let's get a better feel for temperature, critical temperature. Let's go now to table A2, the temperature table for H2O, and let's go all the way down to the last entry in the temperature table. And you see that it's not even an integer. It is, in fact, the last entry. The highest temperature entropy on the temperature table for H2O is 374.14 degrees C. And if I do the math, I'll see that that matches the critical temperature of 647 degrees K. Okay, so now I've got a better physical feel for the critical temperature for H2O. What's the boiling point of water on the stove? At 1 atmosphere, the boiling point of water is 100 degrees C. So at least I have a feel that 374 is really, really hot. It'll really burn you, right? Really hot. Okay. Critical pressure, 220.9. Okay, great. That exactly corresponds to table A1. The critical pressure, critical point, 220.9 bar, or 22,090 kPa, 22,000 kPa, or 22 megapascals, a really high pressure. Let's do one last thing while we're in table A2. Let's look up the critical specific volume. In other words, what is little v? What's little v where that red dot is at the critical point? What's little v? So I'm going to look on my table. There's the last entry. And, and I compare these two numbers. And do you see that these two numbers are numerically identical? Wow, they don't look identical. Oh yeah, they are here because of this pesky 10 to the cubed in the column heading. So 3.155 times 10 to the minus 3, of course, is exactly equal to 0.003155. So I'm going to write down that the critical specific volume, little v crit, well, that equals Vg, and it also equals V sub F. And so a good learning, if you haven't thought about it yet, is at the critical point, V sub G equals V sub F equals 0.003155 for H2O. So now we've got all three properties at the critical point. Let's put them on the PV diagram to get a visibility, a little more feeling for what's the critical point. So I have labeled with numbers on our PV diagram the critical point. So let's see, here's a dashed horizontal line. That's the critical pressure, 22 megapascals, or 22,000 kPa. Okay. How about this purple line, this line of constant temperature that passes through the critical point? I've labeled that as 374 degrees C, a line of constant temperature that goes through the critical point. And then finally, this dashed vertical line, I've labeled it, here's V critical, 0.003155 cubic meters per kilogram. So notice here, I've shown on our PV diagram, you see if I've got a dot over here on the right-hand side of the vapor dome, I'm G, I'm V sub G. And if I'm over here on the left-hand side of the vapor dome, I'm V sub F. And so I think visually now you see that at the critical point, V sub G equals V sub F, and that's how we wrote down 0.003155 cubic meters per kilogram. I sure do hope that gives you a physical feel for the critical point. Now what I'd like to do is take you through an imaginary experiment, maybe to give you a visual feel for what the critical point means. So let's set up this imaginary equipment and experiment setup. I have a saturated two-phase mixture contained in this rigid vessel, and the initial pressure is 100 kPa. 100 kPa, that's about atmospheric pressure, isn't it? So if in our imaginary experiment, if I've got a mixture of saturated liquid and saturated vapor, do you immediately know about what the temperature is inside this vessel? Sure, if it's H2O at 100 kPa, it's boiling, so it's about 100 degrees C. I'm going to propose in our experiment that we add heat. We light a fire underneath this vessel, and we start adding heat to the bottom of this vessel. So we're going to add heat. It's a rigid vessel, so your common sense tells you, you know what's going to happen. We're adding heat. The pressure in this vessel is going to go up and up and up and up. And I'm going to say we're going to keep adding heat until we reach a pressure of 23 megapascals or 23,000 kPa. So we're going to add heat until the pressure goes way up. So we need to have a very stout, rigid vessel here. Okay, so here's the purpose of our experiment. Based on the initial quality of the saturated mixture, we're going to look at 3 different qualities. Will the visible liquid level, this little dashed line, will the liquid level go up, or will it go down, or will it stay the same? And I've taken a little clip out of a YouTube video I'm going to try to chase you to. It might be a little harder to see, so I've put a red dashed line above and below the visible saturated liquid, saturated vapor line in the screenshot. So you can see, visually you can see, get a vision of a real world picture of our imaginary experiment setup. Okay, so this is our purpose of our imaginary experiment. Will the visible liquid level, is it going to go up as we add heat? Is it going to go down as we add heat? Or will it just stay the same? All right. So let's pinpoint state 1. So let's get going with some numbers to try to quantify our experiment. Let's pinpoint state 1. Let's see, we had a saturated mixture. We'll use the pressure table since that was given. We'll go to the pressure table where P1 is 100 kPa, 1 bar. We'll look up the temperature, 99.63 or about 100 degrees C. It's boiling. And let's write down V sub F and V sub G. V sub F is going to be 0.00104. V sub G, 1.694 cubic meters per kilogram. And so we're going to look at 3 different qualities. We're going to have an X1 of some number, and then we're going to change it, and then we're going to change it again, and look at those examples. So V1 is going to be bigger than or equal to V sub F, and it's going to be less than or equal to V sub G because we've got a saturated mixture. Okay, and so we're going to start state 1. So here's our sketch. All these dots represent candidate states for state 1, because it's always going to be under the dome, and which dot we select is going to depend on the value of X that we decide on. So we're going to pick 3 values of X. Quality. Let's do experiment number 1. Let's say that X1 is 0.1%. In other words, 1/10 of 1%. So not 1%, but 1/10 of 1%, a low quality. So can you visualize about where the dot's going to be before we go through the numbers? Well, the dot, it's a low quality, so the dot's going to be somewhere over here, isn't it? Okay. Well, let's do the math. We've got X1 is 0.1%. We wrote down V sub F and we wrote down V sub G. Let's do the math. Well, V1 is going to be V sub F, that little number, plus X times VG minus VF. We'll turn the crank and we get V1 is 0.00274. Let's compare that to V sub F. So it's about double V sub F, isn't it? Let's pinpoint it on the PV diagram. Okay, here's going to be our process. So here's our imaginary experiment result. Okay, we're going to plop down our state near F. Okay, so I've labeled it 0.00274. Let's see where we are relative to the critical point, relative to the critical specific volume. So I've labeled the specific volume at the critical point, 0.003. So here we are, 0.00274. Okay. What's our process going to look like on our PV diagram? We're starting at state 1. We're adding heat at constant volume, rigid vessel. So we're going to be on a vertical line, and we're going to keep adding heat until the pressure reaches 23,000 kPa, or in other words, 2.3 megapascals. I remember that the critical pressure, I think, was around 2.2 megapascals. So my sketch is correct. We're going up over the critical point. Now let's answer the question. What's going to happen to that liquid level in our experiment? Do you see what's going on here? Wow, we're going up through the vapor dome at constant specific volume until at some point we're going to hit the saturated liquid line. Visually, what happens when you're a saturated liquid? You're all liquid. And so that tells me that the liquid level is going to go up for this imaginary experience. It's going to go up and up and up as it's heated. Liquid level is going to increase as it goes up through saturated vapor. So there's experiment number 1. It's kind of a big conclusion. So if your point is to the left of the critical specific volume, then if you add heat at constant volume, your liquid level is going up. Let's do another one. Let's say X is 5%. So now we're going to do experiment number 2. So forget about what you just did. We're going to say X1 is 5%. Well, it's going to be further to the right, isn't it? Okay, a little closer to G. It's not going to be right on the G area, because X would be 0.9 or so if it was here. So it's going to be to the right. Okay, let's do the math. Let's do the math and say V1 in this case is 0.08569. We're just going to turn the crank. X1 is 5%. We get a number, 0.08569. Let's pinpoint that on the pressure volume diagram, plot our process, and study, is our liquid level going up or down for this situation? Well, there we go. And so we've got 5%. Okay, so I'm going to label my specific volume, V1, as 0.086 relative to our V critical, 0.003. So we're to the right of 0.003. So I put it there. We're going to add heat at constant specific volume. Wow, look what's happening here. We're going up in a vertical line until all of a sudden we hit the saturated vapor line. That means we can't see anything inside of our experimental vessel, because it's saturated vapor. You can't see saturated vapor, can you? So the liquid level is going to fall for this situation. It's kind of amazing to me. So for this situation, the liquid level will fall until it just flat disappears at this point, and we continue to heat until we get all the way up to the state 2, and it looks, I'd call that the superheated vapor state. Wouldn't you? Wouldn't you call that state 2 superheated vapor? And you couldn't see it with your eyes. 2 different conclusions for 2 different experiments. Last experiment. Now, I've picked a specific number. Let's say that X1 is 0.12%. In other words, just a little more than 0.1%. Let's do the math. Let's do the math and calculate the specific volume, V1 equals V2. It's 0.003155. That number sounds familiar. Okay, let's see where we land on the vapor dome, under the vapor dome. Sure enough, for a quality of 0.12 for H2O, we're right there under the critical point. And so our specific volume exactly matches the critical specific volume, and we're heating our mixture. Okay. And here's going to be the conclusion. It's kind of interesting. The liquid level is going to fall slightly because your quality, okay, the quality is increasing slightly, okay, as it's going up. But notice here that it's going to go right through the critical point. And at the critical point, there's really not a visible difference between V sub F and V sub G. And so mysteriously, if we could pull off this experiment, things would get hazy and hazy and hazy as we get to the critical point. It would get blurry, and then boom, there's no liquid line even visible at all. So it's kind of amazing. So this is sort of an amazing imaginary experiment number 3. And this is what reminds me of a movie that my thermo professor brought in to illustrate this point. And so I decided to go out and said, gosh, my professor brought in 1973, professor brought in a movie projector and a movie and showed this experiment to us in class. I said, there's got to be some stuff out there on YouTube that's like what I remember from 1973. And so here's what I did. I've got a couple of screenshots to show you. I don't want to go live to take up your time, but to locate the 2 videos that I've looked at, if you go to a YouTube search of critical point phase diagram, you're probably going to be able to find these and more. So for example, I've got a static screenshot of a really cool video. Now, I don't expect you to write down this link. After I publish this video, I am going to try to insert a dynamic link onto this slide so you can click on it, okay? If I'm not able to pull that off, the YouTube channel for this video of liquid helium, so it's not H2O, it's liquid helium, and this experiment, we're starting at 5.4 degrees K. Wow, that is really, really cold. That's cryogenic liquid helium. It's going to be a liquid vapor mixture of helium, and it's on the YouTube channel SciTunes. Hopefully you could find it. And also, and the pressure of this liquid helium in here is about 230 kPa, or in other words, about 2 atmospheres. But it's very cool that you're going to be able to see with your own eyes what I tried to explain for H2O in our imaginary experience. I'm going to try to insert a dynamic link into this so you can see it with your own eyes. Another very cool video is using CO2 and heating it the same way. And the temperature of this CO2, so do you see, I've drawn some dashed red lines, and there's the visible saturated liquid CO2, saturated vapor CO2 situation, starting at a pressure of 7.2 to 7.3 megapascals inside this vessel, starting temperature of, and you can see they did a superb job of 29 degrees C, heating up to about 30 degrees C. It says heating up to 31. And here's the YouTube channel if my dynamic link doesn't work. But anyway, I highly recommend you watch these YouTube videos because you're going to be able to see with your own eyes what I tried to describe in our imaginary experiments. I hope all of that information helps you visualize the critical point in our imaginary experience, and in the YouTube videos, you're going to be able to see, does the liquid level rise or fall? That's a great question for you to see with your eyes. And the answer is, it depends on your starting point relative to your specific volume in the rigid vessel. It depends on where you are under the dome relative to V critical. I hope I've given you a better look at critical point visualization. This gives you an ability to quantify where is the critical point, critical specific volume, critical temperature, critical pressure, okay? Vg equals Vf at the critical point for all substances. And at that point, there's not going to be a clear visual difference between liquid and vapor of the substance. Okay, I hope that helps you give you a little better feel for visualizing the critical point. Hope it gave you some ideas on working underneath the vapor dome and a little more comfortable with processes associated with phase change substances.